Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mail, and I'll be helping moderate today's webinar, End-to-End Machine Learning Workflow Using Julia. In this webinar, we'll present on how to complete a machine learning project, which can be built using Julia. The key steps will be highlighted are pre-processing and data ingestion, performing a hyperparameter search, leveraging distributed computing to accelerate model discovery, building a reproducible process around the complete machine learning workflow, and finally deploying it as a web service. We'd like to have an interactive session today, so please write your questions in the chat. We'll be either address them on the fly or address each question individually following the demonstration. With that said, I'd like to introduce you to today's presenter, Jeremy Bouchard. Jeremy recently joined Julia Computing as a sales engineer. His experience includes algorithmic and technological developments at an investment firm, EvoVest, and spent 8 years developing actuarial algorithms at Intact Financial Corporation. Please welcome Jeremy Bouchard.
Great, thanks Eric for this kind introduction, and welcome to this new webinar about Julia. So for today's webinar, what we're going to explore is a problem that was first provided by the AI Crowd Insurance Pricing Game Challenge. In this machine learning contest, the objective for the participants was to build a prediction of the expected amount of claim that will be filed by the insured during the next year. There were some interesting variations where participants had to have a best competitive pricing compared to the other submissions. But in today's use case, we will simplify a little bit this problem to bring more generality to it. So we will simply put our interest about predicting whether an insured gonna file a claim or not. So we can recognize here a typical logistic regression kind of problem, which is encountered in a wide variety of problems. It can be about the interest about the churn rate when it comes to customer renewal, or the new business counterpart by predicting the conversion rate. In other contexts, we can think as well of credit or risk of default when it comes to lending. And so I think it's a very general use case when it comes to binary outcomes. All the code we'll cover today can be found in the scoring engine demo.gl project found on the Julia Computing GitHub repo. So it's all open source and it comes as a Julia package. There are 4 components we're going to look at. First, the data loading, then we'll spend more time on the pre-processing part, then model training, and finally sharing our work to the outside world with the model deployment. Let's go ahead with the data ingestion. When we are in the Julia world, we're well covered when it comes to importing a wide variety of data formats. Not only because that there's a lot of formats that are covered by packages, but also in terms of performance. Oftentimes, those implementation represent state-of-the-art in terms of speed, and this is notably the case with the one we're interested in today, which is a CSV.gl package, thanks notably to its leverage of multi-threading. So for other tabular data, there's the arrow and feather formats that is well covered, as well as Parquet, HDF5. For SQL connections, they are backend specific implementations. So for the 3 most common ones encountered being the SQLite, Postgres, and MySQL. There's also the XLSX package that is the go-to when dealing with Excel files. And for a more proprietary format, we are also having coverage from for SAS and MATLAB formats. Another note is about connecting and accessing those data. For example, when we are having data that lives in the cloud. So there's the AWS the GL package that has the wide and comprehensive implementation of the AWS APIs. And there's the AWS S3 package as well that provides more synthetic sugar so that there's a more Julia Julian-based kind of experience when interacting with the data on AWS S3 storage. So in this case, for data simple CSV parsing, we can implement a function if we wish, but it's a very lightweight, as you can imagine, and we wouldn't expect anything else from simple CSV parsing. So here we can use the csv.file, specifying a path for parsing that CSV file, and then syncing it into a data frame format. Something nice to note about it is that this data set is not huge, but it's still a 228,000 observations with 26 variables, and such data should be put live in memory in less than a third of a second. So that's it for the data loading part, and let's spend some more time on the core of our subject today, the preprocessing part. It's often said that we are spending 80% of our work about data munging, crouching in a machine learning project. For sure, regardless of whether that statement is accurate or not, there's for sure a lot of time that is spent in data handling. And in Julia, the data frames.gl really is the cornerstone for such operations. There are a couple of verbs that are worth being aware of when it comes to data handling. Those are notably found in the split, apply, combine kind of terminology. So if we look at more specifically at those, there's the group by that is just about grouping our data frame according to a given variable or a vector of grouping variables. Then the combine is about aggregating function. So when we want, for example, to summarize or extract the mean of some variables according to the grouping variables, then we would use the combine verb. There's the select that is about selecting variables or also supporting like transformation on those variables. But it's about keeping only the explicitly stated variables. And when we want to keep the same number of features, but just adding new variables, keeping the same number of rows, then the transform would be the go-to. So this verb takes specify the data frame that we want to transform, and it takes a pair taking an input variable and the other element being the mapping between the transformation function and its resulting output variable name. So I'll immediately move into our code and take a look at how this can look like in our code. So here I went into the preproc flux in the scoring engine demo.gl. That's found in the under the develop folder. So this is the file I've just opened. And I'll first will load a couple of packages that will be useful for today. I will load our data using the function that we've previously mentioned. So here we found this same 228,000 by 26 variables. And here we'll perform just a couple of variables operation that we mentioned. So first the group by, we will group by the policy coverage. So this should result in 4 groups. So here we see 4 groups based on the key policy coverage. Now that we have a group data frame, we'll try the combine verb. So we will perform the calculation of the mean. We'll skip the missing value, and we will perform that transformation on 2 variables, the vehicle age and the vehicle value. So the result is as expected, 4 observations, 1 for each key of the grouping variable, the policy coverage, and we get the mean for the 2 variables of interest. And finally, if we may use the select, then the resulting data frame is, without surprise, the same data frame, but with only the policy coverage and vehicle value as output.
Jeremy, real
Yes.
quick, someone's asked if you can increase the font size just one. I know you had it there, but it's probably difficult to see. But
Oh, great, thanks. Is
appreciate
that
it.
okay? Let me know if this further zoom in would be preferable.
Yep, it looks like it's good. Thank you.
And now for the transform example, we will define the target variable of interest. So what we're going to do is use the claim amount and convert it into 0 if there's no claim, or 1 if the claim amount is greater than 0. And this event variable will take the name event. And we can take a quick look at the distribution that we have here. So essentially, it's more of a rare event. About like 10% of the observations have a claim in their upcoming year. Great. So let's get back to our preprocessing, and we'll now spend a bit more time about the transform verb. Just as a first word of caution, you might have noticed the transform, there's the exclamation point following it. Actually, there's the two forms that can be encountered. Like in everything in Julia world, the exclamation point refers to functions that operate mutations. So the only difference when you encounter this transform with exclamation point means that the transformation, so the addition of the new out variable, will be added to the input data frame. Otherwise, if you don't have this exclamation point, you'll get a copy of the data frame, including the new out variable. So for building our preprocessing, something that will put a special attention is having a pipeline that provides reproducibility. Something that can be overlooked sometimes when building a machine learning pipeline is that we spend our energy on about the model reproducibility. But I think it's worthwhile to consider the preprocessing step as a model by itself. For example, the model takes a matrix of features as an input, and the resulting output would be the score that can be that translates the probability of having a claim, for example. If we take a preprocessing structure, we can think of it as just like a model, but instead of taking some raw data frame as an input and outputting a single score, it will output a new vector of features that have been transformed following the relevant feature engineering. By having this mental model of the preprocessing as a model by itself, it can help build a structure that will be easier to implement and deploy and ensure a complete pipeline starting from the raw input data down to a final score. So for our preprocessing pipeline, we'll look at a couple of transformations. So what we're going to do is that we're going to develop multiple layers of those transformation pairs. Those pairs that it takes the input variable, a transformation, and output a final variable. For example, first simple case will be the density. In our data, we have information about the population and the town surface area. So by themselves, those information are not initially the kind of feature we want to include in the model, as they are kind of arbitrarily defined based on some territory definitions. But the density itself is a objective kind of characteristic. So we'll build a density target feature by defining such transformation that will be compatible with the transform verb of data frame. So we take two input variables as the first element, define the function, the transformation function, density, a function that takes two inputs, population and area, and then the resulting variable is density. And this is the pair that we're going to store in our preprocessing pipeline. Let's look at another little more fancier operation, how to deal with some categorical variable, and more specifically, an ordered categorical variable. We have looked at the policy coverage when we look at our groupings. So these groupings were based on some string. However, there's an ordered logic to them, going from the mid up to the max coverage. So it can be meaningful to map those strings into a number that represent the level of coverage. To do that, we first define a dictionary that performs that mapping between the string and the relevant integer. And then the second step is to define a Polkov map, a function that takes a string as an input and return the mapping from our dictionary. You can notice that the last argument here is an integer 4. That refers to the default that is attributed if the string is not found in the dictionary. So here we're taking a conservative stance that if we don't have a missing an information that was not part of our dictionary, we will assume the worst case scenario. So now we can build a transform compatible transformation with this pair, taking the policy coverage, applying a bi-row Polkov map, and outputting here the same name. So we will override the feature in our data frame with this numerical mapping of our policy coverage. The bi-row function here means that the function will be applied by a bi-row fashion. So the difference with the density previously is that the density was operating on the full vector of data. To do that, we were using the broadcasting operator. So here you can think of the population and the area as being the full vector of information, whereas the function Polkov map acts on a single string rather than the vector of string from the policy coverage. Let's take a step. We'll now take a step further, looking at some normalizing function. This is a pretty simple transformation by itself. It's about subtracting the mean of the feature, and then dividing by its standard deviation. Something that can be tricky, however, is when we think about having a reproducible pipeline. For example, when we are encountering a new observation in production, we cannot apply a normalization on a single observation. Or similarly, when we perform the split between the training and the evaluation data, we don't want to build a normalization based only on the observation found in the evaluation data, given that will fail to be an independently reproducible pipeline. It could be a case where we have some data leakage, for example, in such an instance. So what we want is to have a normalizer that will keep the same mean and standard deviation found in the training data, and apply those same parameters when we encounter new data, whether it is in the evaluation, testing, or live production data. To do that, here we introduce something that we call a functor. What is a functor? It's the combination of a structure, here a normalizer, and a function. So this normalizer is a structure that contains the parameters of interest, the mean and the standard deviation, and we will then define how this normalizer behaves when as a function. When we send a new vector of feature to that normalizer, it will take that feature and subtract its internal mean parameter and divide by its internal standard deviation. So with that, we will have a fully reproducible and consistent way of applying transformation. For those familiar with Flux, the deep learning library in Julia, this is actually the very same strategy that is used, for example, for the dense or MLP layer. It's a layer that is defined just as well as a functor, and it can also help to see how much like the preprocessing can be thought of as a model by itself. And now to tie all this up together, we've defined a lot of layers so far, like with the coverage mapping, the normalizer. So all those layers will be stored in another functor that we call the preproc. And this preproc, how it will behave when we are providing it with a data frame, it will loop over all of those layers and apply the transformation verb from data frames to our data frame. So the result will be a sequence of transformation up to our final preprocessed data frame that will be now ready to send into our machine learning algorithm. Again, let's take a look in practice to all of this. So now here I'm defining normalization features. So this is the list of features that we're going to keep in our final data frame. And it's called norm, as we will apply as well the normalizer that we've just discussed to all of those features. Prior going to the preprocessing, we will split our data with a 90-10 split. So we are now having a data frame train and a data frame eval. Just to have a validation that our preprocessing will be performing as expected, we can take a look at the distribution of the vehicle age. So here you can see that it's around it's skewed and around the 10, let's say, for a mean value. Similarly, we can take a look as well to the driver age, more normally distributed, a little below 60 years for distribution. And now we will build a preprocessing. We will provide the data frame train and the normalization features. The resulting preproc will be the structure that contains the layer of transformations. How do we get there? Well, first, let's take a look at those transformations that we've discussed. So here we have the normalizer. Below we have the density transformation, and we have other mappings. For example, the policy coverage mapping are found here. Same thing for the driver sex. And the second step is to build that stacking of layers. This is done in the preproc.gl script. What is being done in this function is that we're making a copy of the data frame to avoid mutating the original data, and then we initialize a preproc. So that's the structure that contains that vector of data frames transformation. And then we're pushing into that vector of layers. So the first one being this density transformation. So we push the layer as a first layer, this transformation that takes population and town surface area, the density function, and now the name of the resulting variable. And now we go on in that function and we add other layers like the COV mapping, the driver sex mapping, as we've just seen here. So this is the COV mapping. It is itself a pair of transformation. So back to the preproc.gl file, you can see that in the end, we're completing our stack of layers with a normalizer for each of the normalization features. And finally, we're gonna do some treatment for missing values by replacing missing values with zeros. Here, this is a reasonable transformation given that it happens following the application of the normalization transformation. So it means that our data is centered around 0. And in the end, we return that preprocessing. So let's build that preprocessing. The second step here is the adapter. I'll go quickly about that, but the meaning of the adapter is to transform the preprocessed data frame and convert it in a format that is compatible with the machine learning algorithm. So in the case of Flux, the expectation is that the input is a matrix where the first dimension represents the features and the second dimension the observations. With the gradient boosted trees algorithm, it's actually the transposition of that format. So the the input format is expected to be a matrix where the first dimension is the number of observations and the second dimension, the features. So this is the purpose of the adapter here. Now that we have the preproc, we use it in its function behavior. So we pass it input data frame, and it returns a preprocessed data frame. Let's look at the result. Vehicle age. We can see now that the vehicle age distribution is centered around 0, and the driver age, same thing, centered around 0. So now we have a preprocessor object and a model adapter that we can save for further usage in a BSON format. We will actually perform the very same thing with the preprocessing for the graded boosted tree. That will result, that is actually the very same process, but we will give them a different name in case we will be interested in applying different transformations. So now we're ready to move on into model training. So the first model we'll look at is the simple multi-layer perceptron model using Flux, which is the go-to library for deep learning in Julia. The model definition is quite straightforward. You can see the code on the left and the resulting representation on the right of the model we've just defined. So we are using here simple like a dense transformations, as well as the associated activation functions. Here we're using ReLU. And we add some fanciness here with a skip connection that takes in its internal layer will be a dense, and it will then add the resulting dense features to the input features to that skip connections. So the only constraint here means that we need to have 32 outputs for the internal skip connection, and this 32 matches the input of that skip connection's 32 features. Finally, we make a dense layer that projects into a single dimension, so the 32 input and a single one output for this dense final layer. And finally, we perform a reshape. So we transform this 1 by batch size matrix into a vector of length batch size. The reason for this is that we want to have a compatible shape for the resulting output of the Flux model with the target variable. So this target variable will be the 0, 1 information on whether there's been a claim, and this input, the target is of shape, is a vector of length batch size as well.
Jeremy,
now
real quick. Jeremy,
Yes.
real quick, sorry. There was a question from Shake. He says, does BSON, is that more performant than JSON? And is that your recommendation?
Yeah, that would be relevant as the BSON like stores the information about not only like if it would be like in the JSON format, you would store like all the internal like data, but the BSON format is really like a serialization of the whole Flux or Julia object. So when you load it back, you get the actual model, and that's something that needs to be parsed back into your model. So for Flux, that's will be like the recommended way for storing like a Flux model. And it means just a word of caution, like you have to have a compatible format of the package. So if there's breaking changes in your package version, then your BSON might not be compatible following that breaking change in the package. So here again, like the reproducibility about like the package versioning will be worth keeping in mind.
Thank you so much, Jeremy. There's a follow-up question on that. Is it like Pickle and Python? I'm not sure if you're a Python aficionado, but is it like Pickle?
Yeah, I'm aware of the Pickle format, but I couldn't comment about how whether it's different or to what extent it's the equivalent of a BSON or more of a other kind of serialization. So I would have to validate this one, not to not to cut the corner too much about this comparison.
Awesome.
But I think their
Thank
actual
you.
use case will be similar kind of applications for sure. Yeah. So now for the gradient boosted trees, that's an example. Here it's evotrees.gl is a pure Julia gradient boosted tree implementation, and the behavior and the configuration of the model looks very much similar to the other libraries you might be familiar with, whether it's XGBoost, LightGBM, or CatBoost. So essentially, we define a loss, a logistic, a metric for the log loss, and the other parameters are the common one found in the other implementations. Something to note is that there's the NBin that is here, as the evotrees implementation relies on histogram binning. So now we'll look at how we can make our train our hyperparameter search with first the evotrees. Let's look at here. If we go in the develop folder again, I'll open the hyperGB3 serial. And in the script, the element of interest, the first one will be here that we will load our preprocessing assets. Should be okay with that. So what we perform in this preprocessing, in this model training, is that we will load the preprocessing assets that we first defined in our preprocessing step, and here we'll be able to simply call the preprocessor, both for the training and evaluation data, resulting in consistent preprocessed data. The other step is we'll define a fit function. This fit function will be about sending the information on the hyperparameter search of interest. So here we've taken a minimal use case where the hyperparameter search will be over the max depth. So we pass this as an argument to the fit function so that we can define the parameterization of our evotrees model with this max depth. So this could be easily generalized, as you can imagine, by passing a dictionary of a various hyperparameter configuration of interest. The second step is to fit this model using the fit evotree function, and then the function returns the evaluation metrics, the actual information about the hyperparameter that was tested, and the model itself. Now we'll define a list of hyperparameters of interest. So here we have a list of 8 different max depths, and we will then perform an exploration of those 8 hyperparameters through that loop that is applied through the map function. So for each max depth list, we applied a function that is the following: the fit function with the applicable max depth. So let's launch this, and now we will have our hyperparameter search in progress. Now let's take a look at how we've applied this kind of hyperparameter search. What we're doing here is that we first perform a first hyperparameter search. When this will be completed, we'll pass on to the second one until the 8 hyperparameter configurations are completed, and we can then gather the results, figuring out what was the best performing models, and save that best model. But sometimes some large model can take a lot of time to fit, and if we're exploring a large hyperparameter space, it can result in pretty expensive computing resources. For example, let's imagine model training takes an hour, and we are exploring 100 hyperparameters configuration. It turns out that we're dealing with over 4 days of compute. Something nice about cloud resources is that there's not really much any cost difference whether it's having an instance running for 100 hours or having 100 instances running for only 1 hour. So this is a situation where exploiting distributed computing can be a lot of interest. So here's an example where we will instead leverage that distributed computing here on the 8 workers, given that we're dealing with only 8 hyperparameters. So we'll do that using the Flux hyperparameter search. And we will leverage here the Julia Hub capabilities to submit a script as a distributed job. So now I'm opening the HyperFlux script, and we'll look at some of the difference that are involved when it comes to distributed computing. The first one being the usage of the distributed library. And the other one is to make sure that all the functions of interest for the distributed computations are available to our workers. To do that, we can add the everywhere macro prior to calling the library, like we're doing here. And as we can see, now I'm in a VS Code, so I'm not having a distributed setting. The number of workers is 1, but we will look how we can submit such distributed job. I'll first show you the other consideration to have for having a distributed compatible script. Here I'm adding everywhere, again, for the some of the functions that will be used. So the loss definition for the deep learning model. Same thing for the log loss or evaluation metric. I'm doing the same thing for the training loop that will be used. And finally, for the fit function, that is the equivalent of the fit function we've just defined for Evo trees. To the difference, then here we're defining a chain based on the H1. It will be the hyperparameter of interest, so the number of hidden features for the first dense operator. And finally, we'll also have another trick here to send the data to all of our workers. So not only the functions need to be available to the worker, but the data itself. So what we're doing here is that we're using the spawn at to send the X-train, the target for the training, same thing for the evaluation data, to all of the workers. Once that is done, we can now send the same kind of hyperparameter search that we've done for Evo trees, but now using the PMAP. So the PMAP is the equivalent, the distributed equivalent to the mapping function. The only difference is that each of the elements, the iterator on which we operate for here the H1 list will be sent to a different worker. And once this will be performed, we'll be able to aggregate our result and figuring out what is the best performing model and save it. So how we can submit this to as a distributed job, if you have the Julia Hub extension installed, you can go into it and you'll see here that we have some options. We're validating that we're having a valid connection. The first element of interest here is this bundle directory. So that represents the environment that would be loaded. So you can think of this as the package. So it will look at the project.toml and the manifest that specifies the package to be used, and the current file. So here the HyperFlux will be the script we want to run. And then we can define the job characteristics. Here it will be a distributed job instead of a single process job. We'll select a few CPUs to be launched. And the element that we are considering here is to have a process for each of the nodes. And we will launch here 9 nodes. And by having 9 nodes, we will have 8 working process. So that's one working process for each of the hyperparameter configuration. You can set some limit, and then I'll be ready to submit the job. And once this is run, it will result in a tar file that I can untar, and it will contain the saved model, the BSON, as well as the CSV. Oh, I've made a too large bundle right here. So here I've already added the resulting model, the BSON for the model flux and the gradient boosted trees. Same thing, the same folder, assets folder that we've put the adapter and our preprocessing data. So now that we have those 3 components, the preprocessing, the adapter, and the model, we're now ready to share our work with the outside world. To do that, we can build a simple web server that will take and the role of that web server will be to return a score, so the prediction of each of our model based on the raw data submitted to that server. So this is a kind of a reasonable scenario if we assume that the role of that deployment is to take raw input and return a score. So if the raw data that we first worked from in our preprocessing is the same, comes from the same system that will be pinging our scoring service, then that makes some sense to make this assumption that the raw data is in the same format. Here again, it's something to take great care into thinking from where do we start the preprocessing, and starting from the very raw from our system that will be coherent with the actual production system can save a lot of headache when it comes to model deployment. So what we need to do for having a valid web server endpoint is to define a function that will take a HTTP request as an input and gonna return a valid HTTP result. For having such kind of result, the more typical format is a JSON. So what we need to do first is convert the request information into a data frame so that we can apply our preprocessing pipeline and prediction from the model. To do that, we will use HTTP functionalities to read the body of the request. So this is with the http.payload. And then we will use the JSON tree reading format that will then be piped into the JSON table to put it in a format that is compatible with data frame. So the result of this first line is about taking the HTTP query and putting it in this data frame Julia friendly format. The second step is simple. Since we've taken care having a curated complete pipeline, we just need to take the data frame and pipeline it into the preprocessing function, the preproc flux, then the model adapter for flux, finally the flux model itself, and at the very end we add the logit transform. The reason for that is that in our flux model, the last layer was just the dense linear projection. So we need to apply the logit transform so as to bring our score into the probability domain that will be compatible and perhaps more human-friendly and coherent with the output that we get as well from the gradient boosted trees. We can then define the format of the data we want to return. We will define a dictionary that maps the score with the actual score, numeric score. And finally, the HTTP response, 200 valid response, and we're writing this in a JSON format. So to put that alive, we can launch those kind of jobs from our local VS Code. That's possible, but not necessarily practical if we want to make this scoring engine accessible to the outside world. Something we can make is to leverage the on Julia. There's the application that we can add. So to add such application, we simply need to specify a valid URL for our Julia project. So we will here we can put the URL of the scoring engine demo. And the assumption for having an application is that we have a main.gl script into a bin folder. If we have that, then we are able to have an application and to launch this application, just like we did for launching a distributed job. So once this is launched, we can connect to it, and here we get the first entry point mentioning that the service is active. That's a good thing. And how we get to this valid service was something that we defined in our service. Here, I go in the bin and the main script. And the reason we're having this message is that we've defined another function that acts as the entry point for our application. So this is a get query. And here we can see the same score flux that we've described, that we first described, and the same thing for the gradient boosted tree entry points. The remaining steps to have our HTTP server ready is to first define the scoring router, and then we register those entry points. One for the main one that returns the welcome message, and then we make post entry points because we want to submit the data in the body of the query, and this we can do that for the both flux and gradient boosted tree. Once that is done, the only remaining step is to launch the server, define the IP address, and we're good to go. And to validate that this is working, we can ping our service using the HTTP request. So here I'm making a request. Not this one. I'm making I'll do a request to this service right here, and the URL should match the one that we have for our service. So that's the URL of our live application. So if I'm making a query here, you get the result that the service is active. So now let's make a query with 5 observations from our original data. I'll make it for flux. And here we get the 5 metrics, the 5 scores, one for each of the observation. Same thing for gradient boosted trees. And now we can make something a little more ambitious. We can send 100 of such queries, and it should work pretty smoothly. As a final step, I'll just extract the scores as a vector of scores for each of them, and we'll make a little scatter to validate if our 2 models are consistent. And this is reassuring. We have pretty much a high correlation between both predictions, and we can see that it's about around 0.10, which is consistent with when we first look at the histogram showing the distribution of our target data. So the probability of having a claim in the upcoming year, that was around 10%. So that's pretty much the very basic for having a functional router. Something that will be of interest as following steps is to dig further into the diagnosis of our model. That's something we can look for another presentation, notably with the dash.gl or stipple.gl, and also looking at model interpretability with the SHAP diagnosis. But for today, this is all that we wanted to cover. So I'll move on to questions if you have any.
I think luckily we've had some help from Matt Bauman. He's been answering a lot of the questions in the chat. So thank you so much, Matt Bauman, if you're still listening. Certainly appreciate the help. Are there other questions that folks have? If you wouldn't mind just entering them in the chat, we'll be happy to address them.
Yeah, I haven't paid attention to the actual question in the chat. So if there's anything or Matt to chime in for asking questions, but that will be helpful as I've skipped those while presenting.
How about the one from Jonas there, Jeremy? Can you read that one? How would you compare and contrast this end to end in Python?
Oh well, I think there's so many recipes. You know, there's a lot of ways to approach like those kind of pipelines. So I think it would be helpful, like maybe to compare with a specific kind of a workflow you might have in mind in Python. For example, like we've shown some pipelines that were really built from scratch in Julia, to the exception of data frames, but I'm considering data frames as a kind of a core ingredient to the tabular data ecosystem. But there's, for example, in Python, there's this scikit-learn that is very popular, and we have a scikit-learn.gl in Julia as well. And another pure Julia implementation is mlj.gl, which will be kind of a pure Julia counterpart to scikit-learn. So it's something worth considering if you want to look at pre-built recipes and pipeline operators and some other helpers for hyperparameters discovery.
The next one would be from Alan towards the top of your screen that's going away. So the purpose of the router is to interact with the cloud through the Visual Studio or to allow a non-video studio use of the models. Do you see that one? It's a little bit, you need to scroll up a little bit. There you go, right there. Alan Baker.
Okay. Yeah, so the router is, yeah, this is what's kind of convoluted in the presentation because we've kind of put the HTTP server within the project. But the idea here was to represent like how to bring really the analytical work into a production environment. So it's not tied to a VS Code server or anything. You can think of it as, for example, you build a model, and we have those three asset components, the preprocessor, adapter, and model, and we've saved them as JSON. Well, then you can take those assets, put them in another separate like library, and just pin a web server that will just read those three assets, make some endpoints, and now you're having a service that makes that perform the inference, the preprocessing, and the inference of your model. So it's ideally the idea was to show like how to take your internal development ML project and how to, let's say, save those assets in order to have them to live independently in another system and for production usage, for example.
So I think the next one you could probably answer is from Michelle there. What is your opinion regarding http.jl and or versus Genie?
Yeah, so this is kind of like two different level of abstraction. Like Genie does use HTTP as a for its basic HTTP interactions. So HTTP is kind of the basic tool. So if you just want to put a function available, for example, this simple endpoint, and make it available, then HTTP can be sufficient. So Genie is much broader in terms of application. So when it comes to, for example, all the it's about like building like a complete application or a complete web service with the rendering of the pages and integration as well with interactive dashboard with the stipple.gl that sits on top of Genie. So it's kind of more of the difference between just having the bare minimum web server versus having a web development framework, which would be Genie. I think there was Yeah, so I've just looked at regarding the deployment. If there are image of HTTP Genie on Docker Kubernetes for scalability purposes, I'll have to take a look on those. I'm not aware of readily available images on that. Actually, in the scoring engine demo, there's an example of recipes for building this application. The main.gl, so the web service. So there's an example of a recipe for a Docker to build this image, so that you have a Docker image that once you launch, serve that your model. So that can be an example, I think, if you're interested in having this first building block of a Docker image that serves the model. So just for the precision, I think if you are interested in that, it's there's a Docker, and you have there were some tests here, but the Ubuntu should be valid. Or if there's any issue, I haven't updated it in the last week. So if there's an issue, don't hesitate to open an issue on the project, but that should be working.
There's another question from R. Bernal. I don't know if you see that one, Jeremy, but it says, what is criterion to use the loss function you are using? Is it not better to use the cross entropy function? That makes sense?
Yes. So actually, in the binary case, the function that was used was should have been like equivalent to the cross entropy in this binary use case. If I'm hoping I'm not making some mistakes in the interpretation, but if I'm not mistaken, the actual implementation of the loss function was the equivalent of the cross entropy. Actually, would be like the logit cross entropy in the Flux language, because we're using the raw linear projection. So in Flux, if you submit the predictions on the linear domain, then you use the logit cross entropy, so that the Flux loss functions perform internally the logit transform in a more numerical stable way. Oh, thanks. I've just seen some benchmarks about HTTP. Hope that it's positive in terms of performance. I'll be curious to look at that. Thanks for this.
There's one other question I saw further up that says, great presentation, thanks. A bit off topic, but may I ask for references about Julia on ARM MCUs? I don't know if you're familiar with that, Jeremy, and whether you want to address that or.
Yeah, I'm well, I guess for running Julia on ARM CPUs, I'll need to have maybe someone to chime in about if there are some caveats about it. For what I'm aware, it's totally compatible on ARM CPUs, but for the MCUs, I'm not aware. So if someone else can chime in, that would be appreciated.
Yeah, you know what? I've seen a lot of great comments, Jeremy. I don't want to. I'm going to look to wrap it up here, if that's okay with you. I haven't seen any other questions on the board, but there were a lot of great comments on the presentation that you gave today. So thank you very much, Jeremy, for your time and the excellent presentation. For the recorded version of this presentation and our past webinars, you can visit the resources tab on juliacomputing.com. For help with your existing Julia machine learning use case or other work on Julia Hub, please reach out to us at sales@juliacomputing.com. Similar to that ARM MCU question, feel free to reach out to sales@juliacomputing.com. We'd be happy to help field that question and help you out in any way we can. Once again, we are happy to help. Thanks again, everyone, and have a great remainder of your week.